Now is it visible?
Yes, yes, now visible.
Okay, fine. So this complete spec, which is a 4-bit processor, you come up with a behavioral description for this, or a gate level structure would have been developed by you, or the complete design you would have developed. But taking this design further on to automate it, you have two ways to do it. One, you can code it by using any of the standard HDLs, hardware description language. The another option, if your system design is consuming only a handful of transistors, let's assume that you have been given a job of making a standard cell design or an amplifier design, two-stage amplifier design, where the transistor count may not cross 25. Under that case, you can go with schematic. In fact, there are multiple tools to support a schematic level design flow, and this HDL mode of system design is more suited while the number of transistors goes beyond 30, 40, something like this. It can support even billions of transistors. So here you can verbally describe the complete design via a hardware description language. That's what here we stick on to Verilog. Of course, you also have VHDL. Compared to VHDL, Verilog is still more convenient and more suitable for hardware description. In fact, most of the designs uh, or most of the industries follow Verilog, whereas initially the people who are in the research domain and the people who are with the government organizations, they were sticking on to VHDL. Now, even this Verilog has been moved on with system Verilog. Possibly that is the next stage of the Verilog, which support more on verification. So it's slight updation of Verilog with what you call it as system Verilog. Okay, fine. You have described the system using a HDL. Now, after doing that, you need to check the functionality of that system via something called a simulation. Simulation. Now, the simulation is mere a functional verification of it. That is, say, I have made a 4-bit adder. So, what I'm trying to do, I just take, I just assign A to be some 4-bit, B to be some 4-bit, and I see whether the sum and carry is same for all possible combination of my input. So, a simulation is mere a process of verifying the code which you have written, such that if the test input are given, whether it is giving the functional output required by the system. Okay. Up to this, you don't have any relevance with hardware. It's only a behavioral level description of your design and you have tested it. But till now, it doesn't correlate with any of the hardware or completely independent of hardware. Situation is kindly mute independent of hardware. Okay. Once you finish this simulation, once you finish this simulation, you can just go with the process of uh, Paramasivam. Please mute yourself. Okay. So the first, these three stages are purely independent of hardware. Following this simulation, once you have verified that, okay, my system is working for the required functionality, you move on to the next step, what you call it as synthesis. This process is completely hardware dependent. What do I mean by this is you can you can target your design or the code which you have written to any of these hardware. When I say synthesis, this synthesis process can take place in two ways. It can go with something like FPGA based synthesis or ASIC based synthesis. What do I mean by this? When I say synthesis, it's mere conversion of your HDL code into the equivalent gates and their interconnections. So say suppose I have designed 4:1 mux. It lists out, say you are using this many number of AND gate, OR gate, and these are the connectivity between these gates, and this is your input, these are your outputs. And if you try to make this as a hardware, you will require, or your estimated area will be like this, power will be like this, timing will be like this. So it gives an estimated area, power, timing report. Now the question is, while the synthesis is being made, you can make two type of synthesis. As I said, you can just go ahead with FPGA based synthesis or ASIC based synthesis. What is the difference between those two? When do we go for FPGA or when do we go for ASIC? This FPGA is field programmable gate array synthesis. Say, let's assume like this. You have written a code, simulated a code, it's working fine. You went for synthesis that says that you require this many number of gates, this many number of buffers, this much amount of estimated area, power, timing. Now the question is, on what target you are going to fuse these gates in? One option is FPGA, field programmable gate array. This is reprogrammable. That's the benefit out of this. You can reprogram n number of time, and it is being done within very short span of implementing your design. Say I would have been coming up with a novel design for FFT processor or DWT architecture. So immediately I would like to go and fuse it on an FPGA and see whether I am getting the desired result. And say I would have done that for 4-point FFT processor, I would like to extend that for 16-bit FFT processor. So under that case, you go again and alter your code such that it involves 16-bit and again refuse in the same FPGA. All this will take place within couple of minutes. Once your code is ready, you can fuse that in the FPGA board n number of time and functionally verify what is your output. So as far as cost is concerned, it is less cost.
Class online class. Class online class.
Timing is also very less. The time consumption is also very less. Time consumption is also less. But what is the problem in this? Please mute yourself. Participants, while you switch on your mic, please mute yourself. Okay. So what happens with FPGA? In fact, it is more advantageous. As we see here, it is taking very less amount of design time, less amount of cost. But what is the problem with this FPGA? It is not optimized. That's the problem. What do you mean by that? Means this FPGA is nothing but a small IC. In fact, the size of the IC will be something like a stamp size, which in turn made up of what you call it as CLBs, C configurable logic blocks, CLBs. These CLBs can be configured to map your design. Say I would like to make a 4-bit adder, triple carry adder. This CLB will appropriately reconnect itself according to the bitmap which you get synthesized from your code, and this whole IC will act as a 4-bit full adder. Now I would like to change my design and make that something like yeah, up down counter, right? Then again I go and resynthesize this particular code and fuse it on an FPGA. Now my FPGA will be acting something like a storage mechanism with the D flip flop and goes through a counting process. So this is the facility that is available with this FPGA. In fact, every CLB has a facility to compute combinational logic as well as sequential logic. That's the beauty about this CLBs. Fine. As I said, this is the only bottleneck, means it is less optimized. Why it is less optimized? Because already the CLBs are prefabricated. Only thing what I can do, I can go ahead and appropriately connect this CLBs. I can connect the CLBs to make my design. But the point is, this connecting the CLBs may not be efficient. It may not be optimized. So with already pre-existing CLB connections, CLBs, I try to connect my own design to establish my functionality. On the other hand, if I am coming to ASIC, this is application specific integrated circuit. What do I mean by this? Here, this code which has been synthesized is being targeted for a library or standard cell. Standard cells. These standard cells are being developed by fab, like the people who are manufacturing IC. They give that library to universities or the company which is going to fabricate or who is going to design. So our role is, once you make this simulation, your design is good enough. Now you target this standard cell and synthesize it. The output of this will be, say, from the library. To establish your design, you require this many number of NAND gates, say from 4 number of NAND gates, 5 number of NOR gates, 10 flip-flops, things like this. You get a list of components being used for implementing your design from the standard cell library. This is called as a net list. Quite often you would have come across this terminology, net list. So the net list is nothing but list of components that has been used for implementing your design using the standard cells which is available to you. So this standard cell library can be 45 nanometer, 90 nanometer, 180 nanometer. So sometime while you are making design, people who works with ASIC based system design, particularly with CAD and mental graphics or something like Synopsys tool, they used to say like this particular design has been implemented with 90 nanometer technology from TSMC, Taiwan Semiconductor Manufacturing Corporation. So what does that mean is, this fab, TSMC, has issued the standard cell library, which are more optimized, and that has been given to you to establish your design using the standard cell. Right. So once you synthesize using the standard cell library, you get a Packard netlist or a Packard design which is fully optimized. That's the beauty of this. Means, by fully optimized in the sense, I mean to say, it is fully optimized with respect to area, power, timing. And it is a customized design. Means, say, I'm coming up with one processor design which is used by 5G network. So this processor design is particularly applicable only for Apple mobile processor with 5G technology. So it cannot be no shared with anything else, or it cannot be used for other purpose, as we discuss here in FPGA. So the FPGA IC, you can use this as something like no washing machine controller, sometime like AC controller, sometime with FFT processor for image processing. You can keep on reprogramming it, but ASIC cannot be done like that. It's a fully customized, optimized for that purpose only. The design time or turnaround time is long. It takes a long time comparatively with respect to FPGA. In fact, roughly, even if your design process uh, is fast, then also you may require at least around 8 months to 1 year time period to bring up your hardware design. So in that way, it takes a little bit of time. It is highly optimized, and the cost is also high. That's also true. Cost is also high. When can you use this, or when can you go for ASIC? Whenever you have the count, the number of count that need to be manufactured crosses in billions. Say I would like to come up with a new phone model. For that, we made one processor. So that count is expected to be 1 billion, 2 billion that need to be manufactured. Then the best way to do that is ASIC. So the ASIC becomes so cheap that could be delivered in the market. That's all. So this is what we see. Once you finalize the design, you come up with this is called as GDSII. This you call it as Gerber Design System Information Interchange File Format. After you do all the process, in fact, in the ASIC, you have too many process, both in the front end and the back end. In the back end synthesis itself, you can again redivide that to partition, placement, routing. In the routing, you have clock, CTS routing, all this. You have, in fact, an n number of processes. I'm not getting into that. After completion of all that, the final outcome is GDS file, which will be given to the fab people, where the fab people manufacture, pack it, and then it will be in market. So it takes this much amount of time. Whereas for this FPGA, that's all. When once you download your bitmap file, they call this as bitmap file after synthesis, after you do your FPGA synthesis, this will be downloaded in your FPGA. It may be any board, Altera board, or any board which you come across, Xilinx board. You can download this bitmap file, and from there on, once you download, it acts as, or this chip act as, a Pakka device with whatever specification you are given. That's all. So the design time for this particular way of implementation is much more faster. And for all research purpose, academic purpose, you go with FPGA. That's all. So this is our top level overview. Now, where are we going to work for this next 2 days? That is majorly on these two domains, that is this HDL code and simulation up to this point. Why do I restrict up to this point? Yes. In fact, this is where the design requirement or the designer role or designer has a major role to play, beyond which it more like the tool specific. Of course, it also needs some expertise to write a script in all these two cases. Of course, FPGA doesn't require any writing of script, but while you go for ASIC, you need certain scripting commands which need to be done in order to come up with an optimized design. But beyond this process, more of tool oriented, but still that is required. Maybe within this short span of time, we may not be able to do that. We are here to get expertise with HDL code and simulate and check this. For these 2 days, we are going to look into these two only. Yes. Now let's straight away go with the HDL. This is Verilog. One important point on Verilog, a Verilog is a case sensitive language. Means, so Verilog is case sensitive. So if at all you are writing out and OUT, these two are considered as two different variables. So make sure that while naming, you should be very, very conscious. Right. Okay. Now let's go about what is the way how to write a code. Very simple. I'm just following the same IEEE standard. If you go through that, it goes around the 300, 400 pages. But at the maximum, I try to consolidate to the way such that it could be easily understood by everyone and everyone can start writing the coding. I believe you would have all installed your model sim, and the model sim which I have shared, the link which I have shared is student version. You can fill up all those details required asked by that Siemens. It's from Metagraphics. You can download that and install. It's a very easy step to go ahead. Right. So the first thing is, while I start writing a code, something like C, it resembles something like a C. Oh, it doesn't work here. 1 minute. I will open here itself. Yeah, now it's fine. I can write my comments here. Right. So as far as Verilog is concerned, it resembles, most of its constructs resemble something like a C. If the people who are good at C, almost you can learn Verilog within a couple of days. Right. So now let's see what is the way to write a code. Now you know what is the keyword. You have a list of keywords which are being used for a particular purpose. You are not supposed to use those keywords for anything apart from that, like giving the names. So the keywords are module, and when once you write a module, it also comes with n module. It's something like a main program. So what is this module, n module? They are again keywords which are typically same as like starting a program and ending a program. One important point to be remembered here is there is no gap between end and module, and you should not give a full stop. These are some of the common mistakes which I am highlighting. No full stop, no full stop, no gap, no gap. And after this module, you need to have a gap, and this is your user defined. You can give identifier some name. Say suppose I am going to write one mux. So this is the name of the module. This is user defined. But one important point that you need to remember is the name should not start with number. Number or special character. It should always start with some characters. So you can give the name of your choice, But the only thing is you need to take care this name doesn't start with any number or a special character. So module, n module, name identifier. Then you have something called as port list. What is this port list? What is this? Port list. Port list is the list of input and output. The list of input and output. What do you mean by this? I may be having, say, something like this. I'm having a mux. So mux is multiple input, single output. A combinational circuit which has multiple input and single output. Let me assume there are two inputs, x1 and x2, and this is my select line. Yes. So based upon the select line, if select line equal to 0, it will be selecting x1 as my output. Let me keep output as y. So this will be transferred to the output. If I give select equal to 1, so this x2 will be passed as my output. A simple combinational circuit. In fact, I don't know what is there inside this box. Let's assume as of now. So both of my input has been given over here, and based upon the select line, my output is being selected. So if I want to list out what are my port list, then x1, x2 are my port list, y is my port list, s is my port list. So out of the port list, I can number like this: x1, comma x2. The port list are separated by commas: x1, x2, s, and y. So this can follow any order. Means what I mean to say is you can first give output followed by input or input in any combination, nothing matters. Why it doesn't matter? Because I am going to explicitly define here, that is what are my input. Again, input is a keyword, output is a keyword. I am just going to define what are my input and output. Here my input are x1, comma x2, comma s. These are my input, and output is y. Remember, for all code which you write, it should end up with the line terminator. The line terminator is semicolon. So all codes should end up with semicolon here too, right? Except the end module. If the last line is end module, you need not give semicolon towards that. But otherwise, you are expected to give semicolon for all the lines. Okay. So now you have defined module, end module. You have given name for that. You have given a list of port list, which you have defined, uh, which are going to be my input, which are going to be my output. That's all. Then you need to say how this output is being connected with input. So this, up to this block, it's the generic description. That's what you could see here. Module, it ends with the end module, and module name, port list, port declaration. In case if you have parameters, I can assign, say something like this. You want to assign the value of delta at one point of time to be 1.5. The next time you want to keep that as 2. So anywhere, if you can define delta as a parameter, so you need not go ahead and rechange the value of delta all over your program then and there. It is enough if you go there and the parameter alone change that value, it will be used n number of times, right? So that's for parameter declaration. Port declaration followed by parameter declaration. Then you have something called as wire and edge declaration, that is variable declaration. So three declarations are there, very similar to that of your program which you would have, C program where you come across. Now the question is, what is wire? What is edge? When should I declare that as a wire? When should I declare that as a edge? When should I go for a variable? These are the 3 points which we need to know. Now let's see what is a wire. Right. A wire is a one which doesn't have the capability of storing, no storage. Whereas a reg is the one which has the capability to store, can store. Right. But you need not confuse this with the reg which you use, which you define with the flip-flops. Or these are some mechanisms which are meant for storing the result. Of course, it's very close to that one only, but still not exactly the way which you use to define your registers, 4-bit registers made up of the flip-flop. No. So these are the two cases, a wire and a reg. Okay, now, when can I define that as a wire? When can I define that as a reg? Mostly, by default, all signals which you declare that as an input and output is wire. You need not go ahead and declare that as wire W1, W2. Yes, you need not do like that, because by default, every signal which you declare is being considered as wire. Then what is reg? If at all, if you want to declare something as a reg, you need to explicitly go ahead and say that this is reg. Say for the previous example, I would like to write this as output reg y. Why should I do so? Because the output which I take out of this 2:1 mux should be stored and used then and there. The input should always be declared as wire, or even if you don't declare, by default it is a wire. Why input should be declared as wire? This input should be a wire, out should be a reg. Why these norms need to be followed? Because, say, this input comes from some of the input source. If the source input changes, the source value changes, immediately that need to get reflected in my design. It is not like it need to wait till then and then that change whenever I want to initiate or bring that source value, then alone it should not come. Or what I mean to say is, any instant reflection that is happening in the input need to be immediately get reflected in my design. So I declare x1, x2 or any input for this sake should be declared as wire. Reg. Reg is whenever my output is being stored, I would like to take output now or then later. So mostly my output would be declared as a reg. There is nothing wrong. You can also declare your output as a wire, but the condition is you may not be able to store any data in that. That's all. So mostly you will be using these two data sets, either as a reg or a wire. And one more condition where wire is being used. Say this is my black box. Inside this you have some gates, couple of AND gate and one OR gate. So for connecting this, you require some intermediate wire inside. This need to be declared compulsorily as a wire. Or any internal connection within the top module. I call this as a top module. Right? What do you mean by a top module? A top module is a design, topmost design, where the inputs and outputs are being accessed by the user. Means the user can access this x1, x2, y select. But the user cannot go inside this block and access this wire. So wire is an intermediate connection within the design. So that need to be declared as wire. these are called as port, input port, output port. So all the ports need to be declared as either reg or the wires, right? Is that clear? But internally, all intermediate connections should be compulsorily declared as wire. That's all. So now we have seen how to define a module, how to name a module, what do you mean by port list, what are the types of uh, declarations, wire and reg declaration, and variable declaration. You can also go with integer, real, all this. Suppose if you want to define some number with integer, real, you can follow the same norms as you usually do with C, right? So this declarations has been over. The remaining thing is you need to say what are you going to do inside that module. Here comes three styles of writing the code. Three styles of coding, or in fact it is four style. One style mostly it is not being used. We will list out what is that, right? We will go with different styles of writing the coding. Once you finish that coding, you end up with an end module, right? Now let us quickly see what is the three styles of writing the code. Right, three styles. They are called as gate level coding, behavioral level coding, this gate level coding is also called structural level coding, then data flow style of coding. One more is there, as I said, switch level coding. But the point is, this switch level coding is very, very rarely used. In fact, it is not synthesizable. Now, you know what is synthesizable means. The code which is written cannot be converted to a hardware. And it is just only for the sake of writing the code in transistor level. That's what you call it as a switch level coding. That is not at all entertained. Better don't use that code anywhere, right? But still, for the sake of completion, I am just quoting it, right? Among these three, when are we supposed to go for which style of coding? Now, first, let's take gate level coding. Gate level coding, I can go for this style of coding whenever I know the complete structure for that. Say, suppose for an example, I would like to write a code for 2:1 mux. Some people might know the gate level architecture for 2:1 mux. So what is that? You will be having two AND gate, one OR gate, one NOT gate. So this is one of my input. Let it be x1, x2, select, select, and select bar. And these two output has been connected and you get an output Y. This is the structure. But since it is a simple design, I know this. Say I'm asking you to come up with an architecture, gate level architecture for 8-bit FFT processor, then it's really tough for me to draw that, right? Like I have done now. This dotted line indicates the black box. As I said, these are my input ports. This is my output port. Now, this is what I would like to say. This is my wire. Which is my wire? This is my wire, which is not accessible to the user. This is wire 2, which is not accessible to the user. This is wire 3, which is not accessible to the user. So while declaring a signal, I need to declare wire 1, 2, 3 as wires. Whereas x1, x2, I can declare that as a wire. Yes, also I can declare that as a wire. Y need to be declared as a edge. So when can I go to this style of coding? This can be done only if I know the structure. If the structure is very clear to me, I will go for this gate level coding. Okay, I don't know the structure, but still I know what is the equation pertaining to that, or Boolean function pertaining to that particular system which you are building. Say for example, the same 2:1 mux can be written as y equal to x1 s bar x2 s. Can I write like this? So y is nothing but like a s bar plus b y, so bs, same thing, right? So x1 s bar select line bar plus x2 another input select line. This is nothing but just a truth table. You can even correlate that one. X1, x2, select line, and output y. So you, for this you can give all possible combination 0, 0, 0, 1, 1, 0, 1, 1. Again for the select line 0, 1, 0, 1. You can give anything. If this is 0, it will transfer this x1 value to my output. If this is 1, it will transfer x2 value to the output. For this case, it will transfer this value to the output. You can see by substituting x1, x2, and s in this equation, you will get the truth table of y. So this truth table has been simplified as a Boolean function, something like this. So this data flow can be used only when I know an equation pertaining to that particular function which I'm going to implement. So if I know the structure, I go for gate level. If I know the equation, I go for this one. So now the case is, I don't know the equation, I don't know the structure, hardware structure, but one thing I know how it behaves. Say, like a counter, I can say how it behaves. So when once a clock pulse comes, the count increases. If it is 3, if the next tick clock comes, it goes to 4, 5, 6. So like that, it goes up to 15. So I know how it behaves. But the thing is, I don't know what is the equivalent hardware for that, and what is the equation which could bring that as a Boolean expression. Under that case, you can go with this behavioral level of coding. In the sense, you don't know equation, you don't know the structure, but you are aware of the behavior of the circuit. Then you can go for this. The switch level coding, you can go only if the design is in transistor level, MOS transistor level. That's all. Now we are almost done. Now let's extend this discussion. While I write the code, what are the things or what are the constructs which are pertaining to these three models? Yes. If it is gate level, you will be using primitives. What do you mean by primitives? Primitives are list of basic gate function which has been given as a library. Their functionality is already defined. You can directly use as it is. Say for example, I am using one primitive and a1 y okay, A comma B. What does this mean? This and is a primitive, means it is there in my library. Whenever I use this and keyword, what does that do is it go and access the functionality of this AND gate truth table. This has been already defined for all basic gates. I need not go and say explicitly that AND gate means if any one of the input terminal is 0, the output is going to be 0. When both the input are 1, then alone you will be getting the value of 1. I need not go ahead and say this. The reason is this has been already defined for all the gates. Like you have around 10 to 15 gates. So starting from AND, NAND, NOR, XOR, XNOR, all this has been already defined. You know how to build a system, or you know how to make the circuit in the gate level already. Now you need to simply write the code and then go ahead with this. So for all gate level circuit implementation, you are going to follow something called as primitives. So these are called as primitives. Suppose if I would like to write the code for this, say let's assume for I would like to write the code for not n1. What is this n1? The n1 is instance name. What do you mean by that? Of course, it is not mandatory, but you can use this instance name. Say, suppose my design has more than one NOT gate. In order to differentiate which NOT gate, I use this instance name N1, N2, N3. It could be anything. So, not N1 instant name. Then within bracket, here one important rule is that the first variable should be my output, followed by any order of your input. Why it is very precise to say, or why it is very important to put the first terminal as my output, followed by inputs. The reason is very simple. While writing the code for gate level or structural level, you are not going to define explicitly these are my inputs, these are my output, as you do in the module. So while you write a code in primitive level, by default, the first variable is my output, and the second list of variables which follows are my input. The order of the input doesn't matter. It will not change my output. So the order doesn't matter. The thing is, so as far as primitives are concerned, make sure you are writing these keywords. Again, all these are small letter. These primitives are the small letters, and these are my instant name, and these are the port list. Port list, one thing you need to be very conscious, that is, make sure you are using the output first, followed by the list of second. Next, that's all. As far as gate level architecture is concerned, writing the code is concerned, this is the norm which you need to follow. You can very easily write the code. Possibly we will look at the same thing while writing the code. Right, coming to this behavioral level coding, here we use some sort of construct like always, if else, case. These are the three major constructs which we will be using. We will discuss what is what, after we go ahead. And if any of these constructs comes, it's nothing but your behavioral level coding. Right. Next, the third is data flow. When I say data flow, I already said all data flow should be described as equation. When I say equations, it involves variables, operators. Means operator means here it is a multiplication operation, here it is an addition operation. Sometimes you may be using XOR operation, power operation, things like this. So I can simply write a code something like this. The key word here is assign. The construct is assign. So suppose if I want to write a code for this, assign y equal to x1. For multiplication, we use ampersand. This is bitwise AND operation. A ampersand yes. For addition, we use bar, pipe symbol. No, 1. Again, x2 ampersand. This is yes bar. Yes bar is tilt of yes. Here it is yes. That's all. Your coding is over within a single line. So the keyword is you are expected to use assign statement. And one more important point which you need to keep in mind, whenever you use assign statement, the variable on my left hand side should be declared as wire. Compulsory. If you fail to declare that as a wire, then immediately it will give an error while you compile the code. Why it is so? Because it's a data flow statement, which means whenever the values on my right hand side changes, immediately that need to get reflected and computed, and the values need to get reflected in the y at the same instant. That's why this left hand side variable should always be declared as a wire. And one more point here, in the always, say I have written a statement, always at passage of the clock. Then I am giving passage of the clock. If reset equal to 1, y equal to 2 tick binary 0 0. I am simply giving like something like this. One important point that need to be noted here is inside an always block, the left hand side variable should always be a reg. This is more important. I'm just comparing and contrasting, right? So in the case of data flow, an assignment statement, left hand side variable should always be declared as a wire. Inside an always block, right? The left hand side variable should always be declared as a reg. So if you fail to do this, definitely you will have a problem with respect to coding, syntax error, right? That's all. I think almost we have done. Now let us start with the simple coding so that you become familiar with, and we will start writing the coding.
I have a doubt.
Yes.
So while writing a Verilog code, should we follow any one of the coding structure, or we can mix?
No, you can mix. You can mix.
We can mix.
You can mix the different coding style. Still, the compiler will permit you.
Okay, fine.
There won't be any problem in that. Okay. Let's go back to, yeah, here all those things we have seen. I think we have discussed what is a wire, all those declarations. Yes, port declaration we have seen. One more. There is a small difference between vector and array. What is a vector, or what is the difference between a vector and array? Say something like this. I am giving This is my adder. Let me keep it like this. A is one of my input, B is another input. A is of 4 bit, B is of 4 bit. This is an adder. This is my sum, this is my carry. Now, whenever I add n plus n bit in my adder, you are expected to have n plus 1 number of total sum with carry. So this is expected to be 4 bit and this is expected to be 1 bit. So totally it will be 5 bit. Now, if it is a single bit, you have already said input so and so variable, output so and so variable. How do you define, how do you declare this many number of bit? The way to do that is say input, again in a small letter, input 3 down to 0. 3 down to 0, A comma B. This is how you need to define. So what does this mean is A and B, these two variables are having 4 bit starting from 0 is my LSB, bit 3, I mean 4th bit is my MSB. So 3 down to 0 is for declaring this as a vector. Now, when I say vector, it is a one-dimensional multi-bit like this. The same thing, say if I declare like this, A comma B is 3 down to 0, then it becomes an array. What is an array? So just I'm highlighting what would happen if you misplace this position. So that's why sometimes you might not even, while you go through the code debugging, it seems like you have done everything right. But if you misplace, this becomes an array. In fact, it's a memory array. It starts declaring A to be something like this. 4 single bit vector, right? So this is 0, 1, 2, 3, single bit vector. So a vector, sorry, a array is a 2-dimensional memory element. A vector is single dimensional memory element. It's like a vector means 3 bit, 4 bit, but only single row, right? So A is 4 bit means 1010, B is 4 bit means 0010, something like that. But if I place this after this variable, it will be declared as a memory element, something like an array with 1 bit of 4 vectors. So you need to be very, very careful in declaring the bit size. That's all. Otherwise, all the other things are fine. Yeah. The port map by connection, all those things we will do that a little bit late. Okay, one more thing. So as far as Verilog is concerned, it supports 0, 1, X, Z. Means, of course, it is a 9-valued logic like weak 0, weak 1, strong 0, strong 1. Like this, you have n number of things. But as such, while you write a code, these 4 values, 4 logic levels are being permitted. Apart from this 4, it is not right to use any other logics like 0, 1, X and Z. You know very well 0 is 0 voltage, 1 is VDD, X is it's not known, unknown, and Z is high impedance. It is not being connected to either 0 or 1, whereas X, it may be connected, but I am not sure of what is that value. Okay, so yes. In order to represent the bit size, we use some 4-bit, 4-tick binary 0000. What does this mean? This is number of bits, which representation you use. It's a binary, hexadecimal, octal. What is that? What is the corresponding binary representation for this? So this is the general syntax: size, base, tick number, the corresponding number. Okay, I'm just quickly skipping it out. Yeah, let's go to the gate level modeling. Shall we go with gate or yeah, let's go with gate. That's more easy. So the first modeling style, let's go with the gate level modeling style. Look at here. So these are the primitives which I said. This is 2 input AND gate, NAND gate, OR gate, NOR gate, XOR gate, XNOR gate. This is a buffer. This is the NOT gate. Remember, these are the primitive codes which need to be followed by you while writing the code. That's all. All the other things are fine. Now let's start. Like I am just going to write a code in Verilog for a 2:1 mux. So we have already written the diagram. So it has 2 AND gate, 1 OR gate, and this has been connected, and this is going to be. Do you hear me? My internet connection says unstable. Do you all hear me?
Yes, yes, we can hear.
Okay, fine. Right. On top of this, as I said, this is actually the box. Now, these are my port. Now, let me start coding it. Before that, let me give all the wirings. W1 is internal connection. Why I should wire this alone, not this one? Because this portion can be accessed by external port, yes, but this cannot be accessed directly because it passes through the gate. That's the reason I give wire 1. Similarly, this cannot be accessed externally from the port. Similarly, this also. But Y can be accessed output. It's an output port. So let me start writing the code. Module mux 2x1. Port list are x1, x2, s, y, semicolon. Input x1, x2, s. Output y, wires w1, w2, w3. Now still I would like to, now up to this portion declaration everything is over. Now we start coding this. Now let me keep the NAND gate instant name as N1, N2, N3, and of course let me keep the NOT gate to be N4. So let me first do NOT gate. NOT is a function of inversion, right? That is N4. As per the primitives, what is the rule? You should always keep your output first. Here the output is W1 is my output. Input is yes. So the next one, let me use AND gate and N1. N1 is the instant name. Its output is W2. You could see here. This is my W2. So I can code this as W2. Inputs are X1 and W1. And next, let's go with another AND gate and N2. Its output is W3. Input is X2, yes. That's all. Then one more, I have one OR gate that is given as instant name N3, and here the output is Y, inputs are W1, sorry, W2, I think, W2 and W3. Yes, W2, comma W3. Yeah, that's all N module. Now this program will work. Okay, don't keep any full stop over here. You can cross check, right? So now let's construct a project and do this. By the way, you can do half adder and a full adder. After completing this, I will give a circuit to do that. Maybe you can do this. Now let us see how to go about with model sim. Okay, fine. I believe you have already installed it.
One doubt, sir. What
Yes,
is
yes.
that instance name?
You
Can
can
you?
give any name, N1, N2, N3, whatever you give, you can use that.
What is the
So what you
purpose?
are asking, what is the need for that instant name?
Yes, yes.
Yes. Say if I am using multiple gates, then to differentiate, or this N1 is for these two input, this N2 is for these two input, I am differentiating that with instance name. That's all. Otherwise, it doesn't have, I mean, you are free to give any name. Even if you don't give also, it won't give any error.
Okay.
Okay. So just I'm giving model sim because I'm using this 10.1. Go here. The procedures are, in fact, I have kept one working manual for it, but it is again hundreds of pages. I think it's not necessary to do that. Straight away, go to Jumpstart, create a project for, you need to keep the location where you would like to do that. Let me keep, this is Pantech, date is 1-2. Let me keep like this. So remember that is having its location in C Altera, this location. By default, this library will be getting created work library. Leave it as it is. Don't do anything on that. Then copy library mapping. Let this also be no selected. Then give OK. After doing this, right, you can close this. Go ahead. Uh, source. Go to source, new source, Verilog. But provided you should have written the code already. For writing the code, you can use, no, you can open project, Pantech, project file. Yeah, this is the project. Add to project, existing file. Now, once going to this project, you could see C Altera. You have opened this project which you have created. In that, I am going to add file. To add the file, well, in before you should have written the code and kept it as .v file. All Verilog files should be saved as .v file. That also I will show. You go here. I have already kept the coding. So I'm just invoking that code, calling that. Let me go with mux if else case. Oh, equation gate level. Yeah. So make sure you give OK. The moment you give OK, oh, this is having RCB. I have added RCB towards that existing file. Browse. Again, I have my code somewhere here. Wherever you have kept, you can just go to that location. This is mux equation, mux gate. I am just giving OK. Yeah, here it has been. You double click that, you could immediately get the corresponding code on my right hand side. This is the panel general template. The bottom one is called transcripts. 1 minute. You can just push that slightly to the top. Yeah. So this transcripts will tell you what is the operation being carried out then and there. So this is for project, library creation, everything. So the work library has been already created, which I have used earlier. This project, now to this project name, what I have given is Altera. In that location, 13.0, yes, I have created a project name, Pantech 1_2, today's date. To that project, I have included 2 of my files. Now, one important thing, while you name a file name, you always make sure the name which you have given here is same as the file name at this point. In fact, there is no condition like that. But later on, suppose if you are working with some sort of ASIC tools, and if you are writing the script, mostly it demands the module name should be same as the file name. So you have the practice of giving the file name same as the module name. That's all. And it should end up with the .b. So you could see I have written a coding something very similar to what we have written now. Now let me tell you how to write a code. Generally, you can, if you would have installed Node++, you can go here. And once you open this Node++, why I am choosing this Node++? Because it will give difference in the color with respect to keywords and the syntax. That's the reason. So go to the new one. You will get something like this. I'm just showing how to write the code because already we have typed it. I don't want to waste my time. So copy that and you are pasting it here. As such, it will not show any syntax error. There is, it doesn't show any color because you didn't save this. If at all, if I am saving this, go here, save as. To the desktop, if I save this, say I'm giving mux gate 1, let me give like this. But one important point, look at this save file type. In the Notepad++, you have all possible different extension. In that, if you come down, you could see something like Verilog, which is having .b. If it is system Verilog, it has an extension of .sv. If it is VHDL, then you have .vh. Right? System VHDL, it has .svh. So appropriately, you need to use the extension I'm just giving here. That's it. Since it is a Verilog code, automatically it will have mux get 1. It saved with an extension of .v in the desktop. Now, the moment you save it, you could see all the keywords are in blue color. That's the point. Now, definitely it will give an error. Can someone look at what is the error now by seeing this itself? Anyone?
At not, sir, not get.
Yes. At not get, I
Semicolon.
have used the line terminator has not been used. That's the point. Okay, like this, you can have all your coding somewhere and you can create a project as I did in the model sim and call those files over here. Yes. Now select this file. I need to compile. The process involves selecting of this file, go to compile selected. Now this has one error. I already know what is that error is. Okay, I think it has duplicated here. Yeah, so this need to be semicolon. All the other things are fine. Oh, not get is not there. I mean, I think something has mixed up. Okay, that need to end up with a semicolon. I think all the other things are fine. One more mistake is there. Okay, no mistake, right? Yeah, no other. Let's save this and let me go ahead and still try. Compile selected. Now you get a green color line which says that it is free from error. In fact, you can find what is that also. So whenever you get a red color line in the compilation problem, double click on this, go there, and you could see the error that has been listed out. Oh, that has been already removed. Okay, now if I want deliberately, I just make this, save this, again go on compile. Yeah, now go here. Yeah, now you could see this gives an error. This error says that near end module syntax error, line number 9. One important point is, see, if you miss the semicolon, the line number V9, it will show only the next line. So you should not keep on rounding up here alone. So anything with respect to line terminated error, that will show the previous line, not this line. So not previous line, the next line it will show. So here it is showing V9, but the fault is with 8. So you need to end up with the semicolon. So it is expecting a semicolon here. So give that semicolon so that it gets satisfied. That's it. So save as. So compile selected. Once you compile, then you go for simulation. Go to simulate. Start simulation. Right. The moment you give start simulation, it go to the work. In the work, you need to search where is this mux gate. Right. This keyword. Module name alone. Mux gate. Yeah, it's here. Select this and give OK.